In the vast, echoing silence of the cosmos, where the light of distant galaxies travels for billions of years to whisper their ancient stories to us, there are moments when the universe reveals something truly unsettling. Something that doesn't just challenge our understanding, but actively disturbs it. For decades, humanity has gazed upon the heavens, slowly piecing together a grand narrative of creation, evolution, and destiny. We've built models, formulated theories, and charted the course of cosmic history with increasing confidence. But what if the most powerful eye we've ever sent into the void, an instrument designed to illuminate the universe's earliest moments, has instead found shadows where there should be light, and anomalies that unravel the very fabric of our cosmic certainty? Imagine, if you will, the James Webb Space Telescope, a marvel of human ingenuity, a golden oracle suspended 1,000,000 miles from Earth, designed to peer back through the curtain of time to witness the universe's infancy. Its mission: to find the first stars, the first galaxies, to confirm our elegant theories of cosmic evolution. But what if, in its relentless gaze into the deepest past, Webb has seen too much? What if it has glimpsed truths so profound, so utterly unexpected, that they suggest a universe far stranger, far more unsettling than we ever dared to conceive? This isn't a story of triumphant confirmation. It's a tale of cosmic unease. It's about data points that refuse to fit, observations that whisper of fundamental flaws in our most cherished models, and a growing sense among scientists that the universe might be playing a trick on us, or perhaps revealing a deeper, more disturbing reality. Webb was meant to show us the universe's gentle awakening, the slow, majestic unfurling of cosmic structures. Instead, it seems to have found a universe that was already mature, already complex, already disturbingly developed, at a time when it should have been nothing more than a cosmic infant. What if the universe is not what we thought it was? What if the very laws that govern its birth and evolution are incomplete, or worse, fundamentally misunderstood? This isn't just about tweaking a few numbers in an equation. It's about the potential unraveling of our entire cosmic narrative. It's about a telescope built to find answers, instead unearthing questions so unsettling that they reverberate through the very foundations of physics and cosmology. Prepare yourselves, fellow cosmic voyagers, because today we embark on a journey into the heart of these disturbing discoveries. We will confront the anomalies, explore the unsettling implications, and grapple with the possibility that the universe, in its earliest moments, held secrets far darker and more complex than any science fiction writer could conjure. This is a story that will make you question everything you thought you knew about the cosmos. A journey into the profound and the perplexing. And if the thought of peeling back these cosmic layers, of confronting these unsettling truths, sends a shiver of intellectual thrill down your spine, then do me a favor. Take a moment right now to hit that like button. It helps us bring more of these incredible, sometimes disturbing, cosmic stories to light. And it tells me you're ready to dive deep into the unsettling mysteries of the universe with cosmo-depth. Now let's gaze into the cosmic abyss and see what James Webb found when it looked too far. For most of human history, our view of the universe was limited to what our eyes could perceive. Then came telescopes, gradually extending our reach, but always with a fundamental limitation: the speed of light. Light, though incredibly fast, takes time to travel across the vast cosmic distances. This fundamental principle means that when we look out into space, we are inherently looking back in time. The light from the sun takes 8 minutes to reach us, so we see the sun as it was 8 minutes ago. The light from the nearest star, Proxima Centauri, takes over 4 years to arrive. And the light from the most distant galaxies has been traveling for billions of years, offering us a direct glimpse into the universe's ancient past. But there's a catch. The universe is expanding, and as light from these incredibly distant early galaxies travels towards us, its wavelength gets stretched. This phenomenon, known as redshift, shifts the light from the visible spectrum, which our eyes and older telescopes like Hubble are optimized for, into the infrared. Imagine a siren wailing as it approaches and then recedes. Its pitch changes. Light behaves similarly, but instead of pitch, its color shifts. The more distant an object, the greater its redshift, and the further into the infrared its light is stretched. This is where the James Webb Space Telescope enters the scene, not just as an incremental improvement, but as a revolutionary leap in our ability to peer into the cosmic past. Webb was specifically designed to be an infrared observatory. Its massive 6.5-meter primary mirror, composed of 18 hexagonal, gold-coated beryllium segments, is optimized to collect these faint, stretched-out infrared photons. To ensure its own heat doesn't overwhelm these incredibly weak signals, Webb is kept at an astonishingly cold temperature, just a few tens of degrees above absolute zero, shielded by a tennis court-sized sunshield. Positioned 1,000,000 miles from Earth at the second Lagrange point, it enjoys an unobstructed, thermally stable view of the universe. Webb's mission was clear: to find the very first stars and galaxies that ignited after the Big Bang, to witness the universe's cosmic dawn. Scientists expected to see nascent, small, and irregular proto-galaxies, still in the early stages of formation, gradually building up their stellar populations over billions of years, as predicted by our standard cosmological models. It was supposed to be a confirmation of our elegant theories, a visual testament to the gradual, hierarchical assembly of cosmic structures. But what Webb found, as it pushed its gaze further and further back in time, was not a gentle, predictable unfolding. It was something far more developed, far more complex, and frankly, far more disturbing than anyone had anticipated. Instead of faint, struggling infants, Webb began to reveal fully formed, massive galaxies, already brimming with billions of stars, existing at a time when they simply should not have had enough time to grow so large. Some of these galaxies are observed at redshifts corresponding to a mere 300 to 500 million years after the Big Bang, a cosmic blink of an eye. This is like finding a fully grown adult in a nursery, a mature organism thriving in an environment where only nascent forms should exist. These discoveries aren't just minor discrepancies, they are fundamental challenges to the timeline of cosmic evolution, suggesting that the universe was far more precocious and efficient at building its grand structures than our models allowed. The implications are unsettling, forcing us to ask, what if our understanding of the universe's birth and early development is profoundly incomplete, or even fundamentally wrong? To truly grasp the unsettling nature of Webb's findings, we must first understand the cosmic framework that these observations are challenging. The lambda, cold, dark matter model. This is our standard model of cosmology, the prevailing scientific consensus that describes the universe from its fiery birth in the Big Bang to its current vast expanding state. It's a remarkably successful model, explaining a wide array of cosmic phenomena, from the faint afterglow of the Big Bang, the cosmic microwave background, to the large-scale distribution of galaxies across the universe. For decades, Lambda CDM has been our cosmic roadmap, guiding our understanding of how everything came to be. The Lambda CDM model posits that our universe is composed of three main ingredients: about 5% ordinary matter, the atoms that make up stars, planets, and us; about 27% cold dark matter, an invisible, mysterious substance that interacts gravitationally but not with light; and roughly 68% dark energy, an even more enigmatic force driving the accelerated expansion of the universe. According to this model, the universe began with the Big Bang, followed by a period of rapid inflation, and then a gradual cooling and expansion. Gravity, acting on tiny quantum fluctuations in the early universe, began to pull together concentrations of dark matter, forming invisible gravitational wells known as dark matter halos. These dark matter halos are the cosmic scaffolding upon which galaxies are built. In the Lambda CDM narrative, the formation of galaxies is a slow, hierarchical process. Small dark matter halos form first, attracting gas and dust, which then cools and collapses to form the first, relatively small, proto-galaxies. These small galaxies then merge and accrete more matter over billions of years, gradually growing into the majestic spirals and ellipticals we observe in the local universe today. This is often referred to as a bottom-up scenario of galaxy formation. Small structures form first, then combine to build larger ones. The key word here, the one that makes Webb's findings so disturbing, is gradual. The Lambda CDM model explicitly predicts a universe where the earliest galaxies, those existing only a few 100 million years after the Big Bang, should be small, irregular, and still very much in their infancy. They should be struggling to form stars, lacking significant heavy elements, and certainly not exhibiting the mature, massive structures we see in today's universe. The cosmic timeline, dictated by the speed of gravity and the rate at which matter can accumulate, simply doesn't allow for rapid, large-scale galaxy formation so early on. Yet, this is precisely what Webb has found. Instead of the expected faint nascent smudges, Webb is revealing hundreds of galaxies that are already massive, luminous, and seemingly mature, existing at redshifts that place them firmly within the universe's earliest epochs. These galaxies are already boasting stellar masses comparable to, or even exceeding, that of our own Milky Way, which took over 13 billion years to form. This is the cosmic equivalent of discovering a fully grown adult running a marathon just moments after birth. It's a profound violation of the Lambda CDM model's predicted timeline for cosmic structure formation, and it's forcing cosmologists to confront a deeply unsettling question. Is our fundamental understanding of the universe's evolutionary history flawed? The disturbing implication is that either the universe was far more efficient at building galaxies in its infancy than we ever believed, or there's a missing piece in our cosmic puzzle, a fundamental aspect of physics or cosmology that we have yet to uncover. These aren't minor discrepancies. They are observations that strike at the very heart of our most successful cosmological model, threatening to unravel decades of theoretical work and forcing us to reconsider the very nature of reality in the earliest moments of time. The universe, it seems, is not content to merely confirm our theories. It insists on challenging them, pushing us towards a deeper, more complex and ultimately more disturbing truth. So, what exactly did James Webb find that is so disturbing? It's not a single, isolated anomaly, but a cascade of unexpected observations that, when taken together, paint a picture of a universe that defies our carefully constructed expectations. The primary disturbance stems from the sheer number and maturity of galaxies observed in the early universe, an epoch previously thought to be a cosmic nursery for nascent, struggling structures. Imagine looking back to a time just 300 to 500 million years after the Big Bang. According to our Lambda CDM model, this period, often called the cosmic dawn, should have been characterized by the slow, painstaking birth of the very first small galaxies. These proto-galaxies would be irregular, metal-poor, and actively forming stars, but at a modest pace. Instead, Webb has revealed a landscape teeming with galaxies that are already massive, luminous, and remarkably well-formed. Some of these early galactic behemoths boast stellar masses comparable to our own Milky Way, a galaxy that has had over 13 billion years to assemble its stars and structure. This is the first, and perhaps most profound, disturbance. But the anomalies don't stop there. Beyond their unexpected mass, these early galaxies exhibit other disturbing characteristics. Many show signs of significant chemical enrichment. Stars are the universe's alchemists, forging elements heavier than hydrogen and helium in their cores and dispersing them into space through supernova explosions. For a galaxy to be chemically rich, multiple generations of massive stars must have already lived and died, a process that takes considerable time. The presence of these metals in galaxies so young implies an incredibly rapid and efficient cycle of starbirth, death, and recycling. A cosmic assembly line operating at warp speed, churning out stars and heavy elements far faster than our models predict. Furthermore, some of these early galaxies display surprisingly well-ordered structures. While the Lambda CDM model predicts chaotic, clumpy mergers in the early universe, Webb has hinted at the presence of nascent disks and more organized morphologies in some of these ancient systems. The formation of stable, rotating disks requires a period of gravitational settling and dynamic evolution that typically spans billions of years. To see even the beginnings of such organization in galaxies so young is another head-scratching observation, suggesting an accelerated pace of galactic maturation that is deeply unsettling to our conventional understanding. Perhaps most disturbing is the implication for star formation: efficiency. If these galaxies accumulated so much stellar mass so quickly, it means they were converting their available gas into stars with an efficiency that far surpasses what we observe in the local universe, or what our simulations predict for the early cosmos. What physical mechanisms could have driven such a frenzied burst of stellar creation? Was there an abundance of cold gas that cooled and collapsed more efficiently? Were the initial conditions of the universe more conducive to rapid star formation? Or were these galaxies fueled by a continuous, super-efficient infall of pristine gas from the intergalactic medium? These combined observations paint a picture of a universe that was precocious, efficient, and far more complex in its infancy than we ever imagined. The disturbance isn't just that these galaxies exist. It's that their very existence forces us to question the fundamental assumptions embedded within our most successful cosmological model. It's a challenge that cuts to the core of our understanding of cosmic evolution, demanding a re-evaluation of the processes that shaped the universe during its earliest, most formative years. The universe, it seems, had a few unsettling surprises hidden in its deep past, and Webb's golden eye is bringing them to light, one disturbing anomaly at a time. The profound discrepancies between Webb's observations and the predictions of the Lambda CDM model have ignited a fervent debate within the scientific community. This isn't a crisis of science, but rather a vibrant period of re-evaluation, where every assumption is being scrutinized and every possibility explored. The disturbing findings demand explanations, and astrophysicists are proposing several intriguing avenues that could reconcile these cosmic anomalies with our broader understanding of the universe. One leading hypothesis suggests that star formation in the early universe was far more efficient and bursty than previously imagined. Our current models often assume a relatively steady rate of star birth. But what if the conditions in these nascent galaxies were uniquely conducive to rapid, explosive bursts of stellar creation? Imagine vast reservoirs of pristine hydrogen and helium gas, unpolluted by heavier elements, collapsing under gravity without the disruptive feedback from supernovae or active galactic nuclei that can suppress star formation in later epochs. This scenario could allow galaxies to accumulate stellar mass at an astonishing rate, essentially compressing billions of years of star-forming activity into a much shorter cosmic timeframe. The early universe might have been a much more violent and dynamic place, with intense gravitational instabilities driving gas directly into star-forming regions, leading to a quick and brutal assembly of stellar populations. This would mean that the efficiency of converting gas into stars was significantly higher in the early universe, a parameter that our current models might be underestimating. Another avenue of investigation focuses on the properties of dark matter and the initial conditions of the universe. The Lambda CDM model assumes a specific distribution of dark matter halos, which act as the gravitational scaffolding for galaxies. If, however, the initial density fluctuations in the very early universe were slightly larger or distributed differently than our models predict, it could have led to the formation of more massive dark matter halos much earlier. These larger halos would then have provided deeper gravitational wells, capable of attracting and holding more gas, thereby accelerating the galaxy formation process. This wouldn't necessarily mean a complete overhaul of Lambda CDM, but rather a refinement of its parameters, or a deeper understanding of the processes that seeded the universe with its initial structure. Some researchers are even exploring alternative dark matter candidates or interactions. While cold dark matter has been incredibly successful, perhaps there are subtle interactions between dark matter particles or between dark matter and ordinary matter that we haven't yet accounted for. These unknown interactions could influence the efficiency of gas accretion and star formation, leading to faster galaxy growth, A more radical proposal involves modifications to our understanding of gravity itself. While Einstein's general relativity has been incredibly successful, some theories of modified gravity suggest that gravity might behave differently on cosmological scales or in the extreme conditions of the early universe. If gravity was slightly stronger or had a different range of influence in the very early cosmos, it could have accelerated the clumping of matter and the formation of large structures. Such theories are highly speculative and would require robust evidence, but the profound nature of Webb's discoveries warrants exploring even the most unconventional ideas. Furthermore, there's always the possibility that our interpretation of the observational data needs refinement, or that there are observational biases at play. While JWST is an unparalleled instrument, interpreting the faint, red-shifted light from billions of light years away is an incredibly complex task. Are we accurately measuring the stellar masses of these galaxies? Are there biases in our observations that make them appear brighter or more massive than they truly are? For instance, the Malmquist bias suggests that in any flux-limited survey, we are more likely to detect intrinsically brighter objects at greater distances. This means Webb might be preferentially detecting the most luminous and massive galaxies, simply because they are bright enough to be seen. If the universe also contained a vast population of smaller, fainter galaxies that are below Webb's detection limits, then our current picture of the early universe might be skewed towards these overachievers. Another consideration is the presence of active galactic nuclei, AGN. If some of these early galaxies are hosting exceptionally bright supermassive black holes that are actively accreting matter, their light could be artificially inflating our estimates of the host galaxy's stellar mass. While astronomers have techniques to identify and account for AGN emission, it's a constant challenge to accurately separate the light from the central black hole from the light emitted by the stars in the host galaxy, especially for such distant and faint objects. The more powerful the AGN, the more difficult this disentanglement becomes. These potential explanations are not mutually exclusive, and the ultimate solution might involve a combination of several factors. What is clear is that Webb's disturbing findings are pushing the boundaries of our theoretical frameworks, forcing us to consider possibilities we once deemed too exotic, and to embark on a journey into uncharted scientific territory. The universe, it seems, is always ready to surprise us, and with every new observation, we are forced to confront the limits of our knowledge and the boundless mysteries that still await us. The universe, through the eyes of JWST, is revealing itself to be a place of constant surprise, where the most fundamental truths are always open to re-examination. The term disturbing isn't used lightly when describing Webb's findings. It reflects a genuine sense of unease within the scientific community. This isn't merely about refining a model, it's about a potential cosmological crisis, a situation where our most successful and comprehensive theory of the universe, the lambda CDEM model, is facing significant challenges that could necessitate a fundamental re-evaluation of its core tenets. The implications of these early massive galaxies extend far beyond just galaxy formation. They ripple through our understanding of dark matter, dark energy, and the very timeline of cosmic evolution. If galaxies formed much faster and more efficiently in the early universe, It implies that the conditions for structure formation were fundamentally different than what lambda CDM predicts. This could mean that the properties of dark matter are not as cold or as non-interacting as we currently believe. Perhaps dark matter particles have some subtle interactions with each other, or with ordinary matter, that could accelerate the gravitational collapse of matter in the early universe. Or perhaps the distribution of dark matter halos, the cosmic scaffolding, was much denser and more abundant in the early universe than our simulations currently account for. These modifications, while seemingly minor, could have profound effects on the rate of galaxy growth, and if proven true, would require a significant update to our understanding of this invisible cosmic architect. Furthermore, these findings could have unsettling implications for dark energy, the mysterious force driving the accelerated expansion of the universe. While lambda CDM assumes dark energy is a constant, could its properties have been different in the early universe? If dark energy had a different equation of state or evolved over time in an unexpected way, it could have influenced the expansion rate of the early universe, thereby impacting the timescale available for galaxy formation. This would open up a Pandora's box of new physics, challenging our most fundamental assumptions about the nature of space-time and the forces that govern the cosmos. The timeline of cosmic events itself becomes a disturbing puzzle. If massive galaxies were already thriving just a few 100 million years after the Big Bang, what does that imply for the epoch of reionization? This was the period when the first stars and galaxies emitted enough ultraviolet light to ionize the neutral hydrogen fog that permeated the early universe, making it transparent. Our models predict a gradual reionization process driven by the cumulative light from many small, nascent galaxies. But if large luminous galaxies were abundant so early, reionization might have happened much faster and more abruptly than we thought. This would force us to revise our understanding of the universe's earliest luminous sources and their profound impact on the cosmic environment. Perhaps the most disturbing aspect is the potential for new physics beyond the standard model of particle physics and cosmology. If all attempts to reconcile Webb's observations with modified lambda, CDM parameters, or observational biases fail, then we might be forced to consider truly radical solutions. This could involve entirely new particles, new fundamental forces, or even a re-evaluation of the laws of gravity on cosmological scales. Such a paradigm shift would be exhilarating for physicists, but also deeply unsettling, as it would mean that our current understanding of the universe is far more incomplete than we ever dared to imagine. It would mean that the universe holds secrets so profound that they demand a complete overhaul of our scientific worldview. The scientific method thrives on such challenges. It is precisely when observations clash with predictions that the greatest breakthroughs occur. But the initial phase is always one of disturbance, of grappling with the unknown, and of confronting the possibility that our most cherished theories might be flawed. Webb's golden eye is not just showing us distant galaxies, it is reflecting back a disturbing image of our own scientific limitations, pushing us to question, to explore, and to ultimately redefine our place in a universe that continues to defy our expectations. The universe, it seems, is far from a solved puzzle, and its earliest moments are proving to be the most perplexing and perhaps the most disturbing of all. The initial reaction to Webb's earliest, most disturbing findings was a mix of awe, excitement, and a healthy dose of scientific skepticism. When the first papers started emerging, showcasing massive, mature galaxies at redshifts previously thought impossible, many astronomers, true to their rigorous training, questioned the data. Were the photometric redshifts accurate? Could there be contamination from foreground objects? Were the stellar mass estimates reliable? These are crucial questions, and the scientific process demands such scrutiny. However, as more data poured in from various JWST programs, including SEERS, GLASS, and JADES, and as different research groups, using independent methods, began to confirm these anomalous observations, the skepticism gradually gave way to a more profound realization. These findings were real. The universe, in its infancy, was indeed far more precocious and efficient at galaxy building than our models had predicted. This shift from skepticism to acceptance has been a pivotal moment, forcing the community to confront the uncomfortable truth that our cosmic narrative might need significant revision. The scientific community's response has been a flurry of activity, a vibrant testament to the self-correcting nature of science. Theoreticians are scrambling to develop new models and simulations that can account for these early behemoths. Some are exploring enhanced star formation efficiencies, where gas is converted into stars at an unprecedented rate in the early universe. Others are investigating modifications to the properties of dark matter, perhaps allowing for earlier and more massive halo formation. Still others are re-examining the role of feedback mechanisms, the processes by which supernovae and active galactic nuclei can regulate star formation, suggesting that these might have been less effective in suppressing early galaxy growth. Observationally, the focus has shifted towards obtaining more spectroscopic confirmations for these candidate galaxies. While photometric redshifts provide good estimates, spectroscopy offers definitive proof of distance and allows for detailed analysis of a galaxy's chemical composition, star formation rate, and internal dynamics. This is a painstaking process, requiring Webb's most sensitive instruments to stare at these faint, distant targets for many hours. But it is through this rigorous follow-up that the true nature of these disturbing objects will be unveiled. Beyond the immediate scientific challenges, these discoveries carry profound philosophical implications. They force us to confront the limits of human knowledge and the inherent biases in our scientific models. For decades, the Lambda CDM model has provided a comforting, coherent narrative of cosmic evolution. It has been so successful that it almost became dogma, leading some to believe that we were on the verge of a complete understanding of the universe. Webb's findings serve as a powerful and perhaps necessary reminder of scientific humility. The universe is under no obligation to conform to our elegant theories. It simply is, and our task is to listen to what it tells us, however unexpected or disturbing that message may be. This period of cosmic uncertainty is not a sign of scientific failure, but rather a harbinger of profound breakthroughs. It is precisely when our models break down, when observations defy expectations, that the greatest leaps in understanding occur. The unsettling nature of these discoveries is a powerful motivator, pushing us to think beyond conventional wisdom, to explore radical new ideas, and to ultimately forge a more complete and accurate picture of our universe. The disturbance, therefore, is not a cause for despair, but a call to arms for the next generation of cosmologists, inviting them to unravel the deepest secrets of a universe that continues to surprise and confound us at every turn. The journey into the cosmic unknown is far from over. In fact, with Webb's golden eye, it has only just begun to reveal its most disturbing and therefore most exciting chapters. To understand the full weight of these disturbing discoveries, it's crucial to appreciate the meticulous process by which Webb collects and interprets its data. It's not simply taking pretty pictures, it's performing sophisticated astrophysical forensics, dissecting the faint whispers of light from the universe's earliest moments. The journey from a distant photon hitting Webb's mirror to a groundbreaking scientific paper is a testament to human ingenuity and perseverance. The primary instrument responsible for many of these revelations is Webb's near-infrared camera, NIRCAM. NIRCAM is essentially a highly sensitive digital camera, but instead of capturing visible light, it specializes in the infrared spectrum. It observes in multiple filters, each designed to capture light at a specific range of infrared wavelengths. This multi-filter approach is critical for a technique called photometric redshift estimation. Imagine a galaxy emitting light across a broad spectrum. As this light travels through the expanding universe, it gets redshifted. Different spectral features, like the absorption of ultraviolet light by neutral hydrogen, the Lyman alpha forest, or the Lyman break, shift into different infrared filters depending on the galaxy's distance. By observing how bright a galaxy appears in various NIRCAM filters, astronomers can create a spectral energy distribution, SED, essentially a fingerprint of the galaxy's light across different wavelengths. They then compare this observed SED to theoretical models of galaxy light, which are generated for galaxies at different distances and with different properties, e.g., age, stellar mass, star formation rate, dust content. The best fit model then provides an estimate of the galaxy's redshift and consequently its age and distance. This photometric redshift technique is incredibly powerful, allowing astronomers to survey vast numbers of galaxies across immense cosmic distances. However, it's an estimation, and for the most critical or surprising findings, astronomers strive for spectroscopic confirmation. Webb's near-infrared spectrograph, NIRSPEC, and mid-infrared instrument, MIRI, are vital for this. NIRSPEC can split the light from a distant galaxy into its constituent wavelengths, much like a prism. This allows astronomers to identify specific spectral lines, emission or absorption features caused by different elements or processes within the galaxy. These spectral lines act as precise cosmic barcodes, providing an unambiguous measurement of the galaxy's redshift and revealing detailed information about its chemical composition, gas kinematics, and star formation activity. For instance, the detection of strong emission lines from oxygen or neon in a very high redshift galaxy would be a direct indicator of rapid chemical enrichment and vigorous star formation, further solidifying the disturbing picture of an already mature system. The initial findings of these disturbing galaxies often come from large-scale survey programs like CEERS, Cosmic Evolution Early Release Science, GLASS, Grism Lens Amplified Survey from Space, and JADES, JWST Advanced Deep Extragalactic Survey. These programs are designed to use Webb's full suite of instruments to systematically map and characterize the early universe. The Sierra survey, for example, targeted a well-studied region of the sky, allowing for direct comparison with previous Hubble observations, which dramatically highlighted the discrepancies. The JADES program, on the other hand, is pushing Webb to its absolute limits, conducting ultra-deep observations to find the faintest and most distant galaxies, some existing just 300 million years after the Big Bang. The sheer volume of data generated by Webb is immense, requiring sophisticated computational pipelines and advanced statistical analysis. Astronomers are not just looking for individual bright spots, they are performing statistical analyses on populations of galaxies, searching for patterns and trends that challenge the lambda CDM predictions. The fact that multiple independent research teams, using different observational strategies and analysis techniques, are consistently finding these unexpectedly massive and mature early galaxies lends significant weight to the disturbing nature of these discoveries. It suggests that these aren't just isolated anomalies or statistical flukes, but rather a widespread phenomenon that demands a fundamental re-evaluation of our cosmic narrative. The universe, through Webb's golden eye, is revealing its secrets, and those secrets are proving to be far more complex and unsettling than we ever imagined. Among the more radical, and perhaps most disturbing, explanations proposed for these precocious galaxies is the concept of dark stars. This theory, while still speculative, offers an intriguing way to account for the unexpected luminosity and mass of these early objects without necessarily violating the lambda CDM model's timeline for ordinary star formation. Imagine a star not powered by nuclear fusion as our Sun is, but by the annihilation of dark matter particles within its core. This is the essence of a dark star. The idea of dark stars emerged even before Webb as a theoretical solution to the problem of the very first stars, the population 3 stars. These theoretical stars were expected to be massive, short-lived, and metal-free, but their formation and properties are still largely unconfirmed. The dark star hypothesis suggests that in the very early universe, when the density of dark matter was much higher, pockets of ordinary gas collapsing to form stars could have trapped significant amounts of dark matter. If these dark matter particles were their own antiparticles, or if they interacted in a way that led to self-annihilation, this process would release enormous amounts of energy. This energy, instead of nuclear fusion, would heat the ordinary gas, preventing it from collapsing further and forming a conventional star. Instead, it would create a massive, puffy, and very luminous object, a dark star. These hypothetical stars could grow to be incredibly massive, perhaps hundreds of thousands or even millions of times the mass of our Sun, and shine with the luminosity of millions of suns, all powered by the slow burn of dark matter annihilation. Crucially, they wouldn't rely on the slow process of nuclear fusion, nor would they require the prior chemical enrichment of the universe, making their existence plausible in the earliest epochs. The disturbing aspect of dark stars, in the context of Webb's findings, is that they could mimic the appearance of massive early galaxies. A single superluminous dark star, or a cluster of them, could easily be mistaken for a collection of conventional stars forming a galaxy. Their immense brightness would make them visible to Webb at extreme redshifts, and their large effective mass could explain why these galaxies appear so massive so early on. If such objects existed, they would fundamentally alter our interpretation of the early universe, meaning that what we are seeing as early galaxies might in fact be something entirely different, something powered by the very dark matter that we struggle to detect. This theory is still in its nascent stages, and direct observational evidence for dark stars is lacking. However, the unexpected nature of Webb's observations has breathed new life into such radical ideas. If dark stars were indeed common in the early universe, they would have played a crucial role in the epoch of ionization, providing an early source of photons to ionize the neutral hydrogen fog. They could also have been the seeds for the first supermassive black holes, as their massive remnants after their dark matter fuel ran out could have collapsed directly into black holes. The implications are profound and, for some, deeply unsettling. It would mean that a significant portion of the light we are detecting from the early universe is not from conventional stars and galaxies as we understand them, but from an entirely new class of object, powered by the mysterious dark matter that constitutes the majority of the universe's mass. It would force us to reconsider the very definition of a galaxy in the early cosmos, and to embark on a quest to differentiate between these hypothetical dark stars and conventional stellar populations. The universe, through Webb's disturbing findings, is pushing us to consider that the familiar might be alien, and that the light from the cosmic dawn might hold secrets far more exotic than we ever dared to imagine. As if the early massive galaxies weren't disturbing enough, Webb's findings arrive at a time when another profound cosmological puzzle is already vexing scientists: the Hubble tension. This is not a direct observation from Webb, but a persistent and growing discrepancy in the measured expansion rate of the universe, and it hints that our lambda CDM model might be fundamentally flawed, not just in its predictions for early galaxy formation, but in its very parameters. The Hubble constant, H0, is a crucial number in cosmology. It tells us how fast the universe is expanding today. For decades, astronomers have been trying to measure it with increasing precision. There are two primary ways to do this. One method involves observing the cosmic microwave background, the faint afterglow of the Big Bang. By analyzing the tiny temperature fluctuations in the CMB, cosmologists can infer the universe's expansion rate in its infancy, and then extrapolate that rate forward to the present day using the lambda CDM model. This method, primarily using data from the Planck satellite, yields a value for H0 of around 67.4 kilometers per second per megaparsec. The second method involves measuring the distances to nearby galaxies using a cosmic distance ladder. This ladder starts with precise measurements of pulsating stars called Cepheid variables, whose intrinsic brightness is known, allowing astronomers to calculate their distances. These Cepheids are then used to calibrate the distances to Type 1a supernovae, which are incredibly bright and can be seen across much larger cosmic distances. By observing these supernovae and their redshifts, astronomers can directly measure the current expansion rate of the universe. This method, championed by Nobel laureate Adam Rees and his team, yields a value for H0 of around 73.0 kilometers per second per megaparsec. Notice the problem? There's a significant difference, a tension between these two values, approximately 9%, that cannot be explained by observational errors alone. This is the Hubble tension, and it's a major headache for cosmologists. It suggests that either there's a systematic error in one of the measurement techniques, which seems increasingly unlikely given the rigor applied to both, or, more disturbingly, that our lambda CDM model is incomplete or incorrect. Something fundamental is missing from our understanding of the universe. Now, how does this connect to Webb's disturbing early galaxy findings? Both anomalies point to a similar conclusion. The universe might have evolved differently than our standard model predicts. If the early universe was capable of forming massive galaxies much faster than expected, it suggests that the physics governing that epoch might have been more complex or different from what we assume. This could, in turn, have an impact on the universe's expansion history, potentially influencing the value of H0 derived from the CMB. For instance, some proposed solutions to the Hubble tension involve modifications to the early universe physics, such as new forms of dark energy, additional relativistic particles, like early dark energy, or even a slightly different expansion history immediately after the Big Bang. If any of these modifications were true, they could also impact the conditions for galaxy formation, potentially allowing for the rapid growth of the early galaxies Webb is observing. The two problems, while seemingly distinct, might be two sides of the same cosmic coin, both whispering of fundamental physics beyond our current grasp. The second method involves measuring the distances to nearby galaxies using cosmic distance ladder. This ladder starts with precise measurements of pulsating stars called Cepheid variables, whose intrinsic brightness is known, allowing astronomers to calculate their distances. These Cepheids are then used to calibrate the distances to Type 1a supernovae, which are incredibly bright and can be seen across much larger cosmic distances. By observing these supernovae and their redshifts, astronomers can directly measure the current expansion rate of the universe. This method, championed by Nobel laureate Adam Rees and his team, yields a value for H0 of around 73.0 kilometers per second per megaparsec. Notice the problem? There's a significant difference, a tension, between these two values, approximately 9%, that cannot be explained by observational errors alone. This is the Hubble tension, and it's a major headache for cosmologists. It suggests that either there's a systematic error in one of the measurement techniques, which seems increasingly unlikely given the rigor applied to both, or, more disturbingly, that our lambda CDM model is incomplete or incorrect. Something fundamental is missing from our understanding of the universe. Now, how does this connect to Webb's disturbing early galaxy findings? Both anomalies point to a similar conclusion. The universe might have evolved differently than our standard model predicts. If the early universe was capable of forming massive galaxies much faster than expected, it suggests that the physics governing that epoch might have been more complex or different from what we assume. This could, in turn, have an impact on the universe's expansion history, potentially influencing the value of H0 derived from the CMB. For instance, some proposed solutions to the Hubble tension involve modifications to the early universe physics, such as new forms of dark energy, additional relativistic particles, like early dark energy, or even a slightly different expansion history immediately after the Big Bang. If any of these modifications were true, they could also impact the conditions for galaxy formation, potentially allowing for the rapid growth of the early galaxies Webb is observing. The two problems, while seemingly distinct, might be two sides of the same cosmic coin, both whispering of fundamental physics beyond our current grasp. The disturbing implication is that the universe might be undergoing a cosmological phase transition, or that there are new fundamental particles or fields at play that we have yet to discover. It's not just that our models are slightly off, it's that the entire framework might be missing crucial components. The Hubble tension and the early galaxy problem, taken together, suggest that the universe is far more dynamic and complex than we had assumed, particularly in its earliest moments. Webb, by peering so deeply into this critical epoch, is not just finding disturbing galaxies, it's inadvertently shining a light on a much broader cosmological crisis, forcing us to reconsider the very foundations of our cosmic understanding. The universe, it seems, is not just expanding, it's expanding our minds, whether we like it or not. To truly appreciate the magnitude of the disturbance caused by Webb's observations, it's helpful to place it within the grand tapestry of scientific history. Science, contrary to popular belief, is not a static collection of facts. It is a dynamic, self-correcting process, a continuous dialogue between observation and theory. Throughout history, our understanding of the universe has been punctuated by moments of profound crisis, where new data has shattered established paradigms, forcing humanity to rethink its place in the cosmos. Webb's findings are, in many ways, echoing these historical paradigm shifts, reminding us that the universe is under no obligation to conform to our elegant models. Consider the Copernican revolution. For over a millennium, the geocentric model, with Earth at the center of the universe, was the accepted truth. It was supported by philosophical arguments, religious doctrine, and seemingly by direct observation. The sun, moon, and stars appeared to revolve around us. But meticulous observations, particularly by astronomers like Nicolaus Copernicus, Tycho Brahe, Johannes Kepler, and Galileo Galilei, began to reveal discrepancies. Planetary motions, especially their retrograde loops, were incredibly complex to explain within the geocentric framework. The heliocentric model, placing the sun at the center, offered a far simpler and more elegant explanation. This wasn't just a change of address for Earth, it was a fundamental shift in our cosmic perspective, a humbling realization that we were not the center of everything. Another profound shift came with Einstein's theories of relativity. Newtonian mechanics, which had reigned supreme for over 2 centuries, provided an incredibly accurate description of motion and gravity for everyday phenomena. But as scientists began to probe the very fast and the very massive, anomalies emerged. The precession of Mercury's orbit couldn't be fully explained by Newton's laws. Experiments with light, like the Michelson-Morley experiment, suggested a constant speed of light, regardless of the observer's motion, which was incompatible with classical physics. Einstein's special and general theories of relativity provided a revolutionary new framework, redefining space, time, gravity, and energy. It was a disturbing realization that our intuitive understanding of these fundamental concepts was deeply flawed, and that the universe operated on principles far stranger than we could have imagined. Even closer to our current cosmic narrative, the discovery of the expanding universe by Edwin Hubble in the early 20th century was a seismic event. Before Hubble, the prevailing view was that the universe was static and contained only our Milky Way galaxy. The concept of other galaxies, let alone a universe that was growing, was almost unthinkable. But Hubble's meticulous observations of distant nebulae, combined with Vesto Slipher's measurements of their redshifts, revealed a startling truth. Almost all galaxies were moving away from us, and the further away they were, the faster they receded. This observation led directly to the Big Bang Theory, transforming our understanding of cosmic origins and evolution. It was a disturbing realization that the universe had a beginning, and that it was not static, but a dynamic, ever-changing entity. Webb's current discoveries, particularly the existence of massive, mature galaxies in the early universe, are creating a similar moment of scientific reckoning. Our lambda CDM model, like the geocentric model or Newtonian physics before it, has been incredibly successful. It has provided a coherent narrative for cosmic evolution and has been validated by a vast array of observations. But now, Webb is presenting us with data that simply doesn't fit neatly into this established framework. The universe, in its earliest moments, appears to be behaving in ways that our most sophisticated theories cannot fully explain. This is not to say that lambda CDM is wrong, just as Newtonian physics isn't wrong for describing everyday phenomena. Rather, it suggests that our model might be incomplete, or that it might be an approximation that breaks down under certain extreme conditions. In this case, the extreme conditions of the very early universe. The disturbance is not a failure of science, but a sign of its vitality. It is a powerful reminder that our quest for knowledge is an ongoing journey, filled with unexpected twists and turns. The universe, through Webb's golden eye, is once again challenging us to expand our minds, to question our assumptions, and to embrace the thrilling, sometimes unsettling possibility that there is always more to learn, always deeper truths to uncover. These are the moments when science truly advances, when the disturbing becomes the catalyst for profound new understanding. This era, ushered in by the James Webb Space Telescope, is truly a golden age for cosmology. The very questions posed by these disturbing galaxies are not roadblocks, but rather signposts pointing towards uncharted territories of scientific inquiry. The challenges they present are not insurmountable. They are invitations to innovate, to rethink, and to push the boundaries of what is known. This is the essence of scientific progress, a continuous cycle of observation, hypothesis, testing, and refinement. And the current cycle, fueled by Webb's revolutionary data, promises to be one of the most exciting in the history of astronomy. The future of cosmology will undoubtedly involve a multifaceted approach. On the observational front, continued deep field surveys with JWST will be crucial, not just to find more of these early galaxies, but to characterize their properties with even greater precision. This includes obtaining more spectroscopic redshifts to confirm their distances and stellar masses, and to probe their chemical compositions in detail. We need to understand if there are systematic differences in their star formation histories or elemental abundances compared to galaxies in the later universe. Furthermore, Webb's ability to peer through dust will be vital in uncovering any obscured star formation that might be contributing to their rapid growth. Complementing Webb's observations will be the next generation of ground-based telescopes. While they cannot match Webb's infrared sensitivity for the most distant objects, their immense collecting areas and advanced adaptive optics will allow for high-resolution studies of slightly less distant, but still early, galaxies. These telescopes will be instrumental in mapping the distribution of gas and dark matter around these nascent structures, providing crucial context for their formation environments. The synergy between space-based and ground-based observatories will be key to painting a complete picture. On the theoretical side, cosmologists are already hard at work. New simulations are being developed that incorporate more extreme star formation efficiencies, different dark matter models, or modified gravitational physics. These simulations will attempt to reproduce the observed properties of these early galaxies, and if successful, they will provide concrete predictions that can be tested with future observations. The interplay between theory and observation is a dynamic dance, with each informing and challenging the other, driving us closer to the truth. Beyond the immediate implications for galaxy formation, these discoveries also open up broader questions about the fundamental parameters of the universe. Could the Hubble constant, which measures the universe's expansion rate, be slightly different in the early universe compared to its current value? Are there subtle variations in the cosmic microwave background that hint at a more complex initial state? These are not minor adjustments. They are questions that could reshape our entire cosmological model, leading to a more nuanced and accurate understanding of the universe's birth and evolution. Ultimately, the disturbing galaxies are a gift to science. They are a cosmic enigma that forces us to think bigger, to question deeper, and to explore further. They remind us that the universe is not a static textbook, but a living, breathing entity, constantly revealing new layers of complexity and wonder. And as we continue to peel back these layers, we are not just learning about galaxies. We are learning about the very fabric of reality, about the forces that shaped everything we know, and about our own place in this grand, unfolding cosmic drama. The adventure of discovery continues, and with every new photon captured by Webb, the universe whispers another secret, inviting us to listen, to learn, and to be amazed. One of the most critical and disturbing implications of Webb's early galaxy discoveries lies in their profound impact on our understanding of the epoch of Rayonization. This period, spanning from about 150 million to 1 billion years after the Big Bang, marks a pivotal transition in the universe's history. Before this epoch, the universe was largely filled with neutral hydrogen gas, a dense, opaque fog that effectively blocked ultraviolet light. It was a cosmic dark age, where the nascent light from the first stars and galaxies struggled to penetrate the pervasive gloom. The epoch of Rayonization is when this fog began to lift, as energetic ultraviolet photons from these early luminous sources ionized the neutral hydrogen, transforming the universe into the transparent, largely ionized state we observe today. Our traditional lambda CDM models prior to Webb painted a picture of a gradual reionization process, primarily driven by the cumulative light from a vast population of small, faint, and relatively numerous galaxies. These galaxies, slowly forming and emitting UV photons, would have gradually carved out bubbles of ionized hydrogen that eventually merged, clearing the cosmic fog. The timeline for this process was thought to be relatively extended, with Rayonization completing around 800 million to 1 billion years after the Big Bang. However, Webb's discovery of massive luminous galaxies existing much earlier, some as early as 300 million years post-Big Bang, throws a wrench into this elegant narrative. If these colossal galaxies were already shining so brightly and forming stars so efficiently in the deepest past, they would have been prodigious sources of ionizing photons. This raises a deeply disturbing question. Could reionization have occurred much faster and more abruptly than we previously thought? If so, it implies that the early universe was far more efficient at producing the necessary ultraviolet light, challenging our models of how the cosmic fog was cleared. The disturbance here is twofold. Firstly, if these massive galaxies were the primary drivers of reionization, it means that the contribution from the myriad of smaller, fainter galaxies might have been less significant than previously assumed. This would require a re-evaluation of the relative roles of different galaxy populations in shaping the early universe. Secondly, a more rapid reionization could have profound consequences for the thermal history of the intergalactic medium and the subsequent formation of galaxies. A hotter, earlier ionized medium could have suppressed the formation of smaller galaxies, creating a feedback loop that further complicates our understanding. Furthermore, the properties of the neutral hydrogen itself during this epoch are also under scrutiny. Observations of distant quasars, incredibly bright active galactic nuclei, provide probes of the neutral hydrogen fraction at different times. These observations suggest a reionization history that is still being debated, with some data points hinting at a later completion than would be implied by an abundance of very early, massive galaxies. This creates a tension. If there were so many powerful sources of UV light, why did reionization not complete even earlier? Some theories suggest that these early massive galaxies might have been so dense with gas and dust that a significant fraction of their ionizing photons were trapped internally, unable to escape and contribute to reionization. This would mean that despite their luminosity, their effective contribution to clearing the cosmic fog was limited. However, this explanation itself requires specific physical conditions within these galaxies that are not easily accommodated by standard models. The epoch of reionization is a complex interplay between the first luminous sources and the pristine gas of the early universe. Webb's disturbing findings are forcing us to reconsider the very nature of these first light sources, their abundance, their efficiency, and their impact on the cosmic environment. It's a reminder that our universe's history is not a simple, linear progression, but a dynamic and often surprising saga, where the earliest chapters are proving to be far more eventful and unsettling than we ever dared to imagine. The clearing of the cosmic fog, once thought to be a gentle sunrise, might have been a much more violent and abrupt event, driven by these precocious galactic behemoths. As if the rapid formation of massive galaxies wasn't disturbing enough, Webb's golden eye has also cast an unsettling light on the early lives of supermassive black holes, SMBHS. For decades, the prevailing theory has been that galaxies and their central supermassive black holes co-evolve, growing in tandem over billions of years. The mass of a galaxy's central black hole is typically found to be tightly correlated with the mass of its host galaxy's bulge, suggesting a deep, interconnected relationship. But the early universe, as revealed by Webb, seems to be challenging this elegant picture in a profoundly disturbing way. Our standard models suggest that supermassive black holes begin as seeds, either remnants of the first massive stars, stellar mass black holes, or direct collapse black holes formed from vast clouds of gas. These seeds then grow over time by accreting gas and dust from their surroundings and by merging with other black holes. This growth process is thought to be relatively slow, especially in the early universe where the availability of gas and the efficiency of accretion might have been limited. We expected to find relatively small, nascent black holes in the centers of these early proto-galaxies. However, Webb has found evidence of exceptionally massive and active supermassive black holes existing within these early galaxies, some as early as 400 to 500 million years after the Big Bang. These black holes are not merely present, they are actively accreting matter at prodigious rates, shining as incredibly luminous quasars or active galactic nuclei, AGN. Some of these early SMBHs are estimated to be millions or even billions of times the mass of our Sun. The disturbing question is, how did they grow so large, so fast? This rapid growth challenges our understanding of black hole seed formation and accretion physics. If they started as stellar mass remnants, they would have needed to accrete matter at an almost impossibly high rate, continuously, for hundreds of millions of years, often exceeding the theoretical Eddington limit, the maximum rate at which a black hole can accrete without blowing away its surrounding gas with radiation pressure. This suggests either that the Eddington limit was somehow circumvented in the early universe, or that the black hole seeds themselves were already massive, perhaps formed directly from the collapse of supermassive gas clouds, bypassing the stellar mass phase entirely. The existence of these gargantuan black holes so early in cosmic history has profound and disturbing implications for galaxy evolution. Supermassive black holes are known to exert a powerful influence on their host galaxies through a process called feedback. As they accrete matter, they launch powerful jets of particles and radiation and drive strong winds that can heat and expel gas from the galaxy. This feedback can suppress star formation, effectively regulating the growth of the galaxy. If these massive black holes were already active so early, their feedback could have played a significant and perhaps unexpected role in shaping the very first galaxies. Could this feedback be part of the explanation for the rapid star formation observed in some early galaxies by compressing gas in certain regions while expelling it from others? Or could it be that the early universe allowed for a period of rapid, uninhibited black hole growth before feedback mechanisms became dominant? The disturbing truth is that the co-evolutionary relationship between galaxies and their central black holes, once thought to be a gradual, well-understood dance, appears to have been a much more chaotic and accelerated affair in the cosmic dawn. Webb's observations are forcing us to reconsider the very mechanisms of black hole growth and their intricate connection to galaxy formation. It suggests that the early universe was not just a fertile ground for rapid galaxy assembly, but also a crucible for the swift emergence of cosmic behemoths at their centers. These disturbing findings point to a universe where the most powerful gravitational engines were already roaring to life, influencing their surroundings in ways we are only just beginning to comprehend. The interplay between these early, massive galaxies and their precocious supermassive black holes is yet another layer of cosmic complexity, adding to the unsettling picture of a universe that consistently defies our expectations. When we gaze into the deepest reaches of the cosmos with Webb, we are essentially looking at tiny, pencil-thin slices of the universe. The fields of view, while incredibly sensitive, cover a minuscule fraction of the total sky. This brings us to a crucial concept in cosmology: cosmic variance. Cosmic variance refers to the statistical uncertainty that arises because we can only observe a single universe. We cannot run the experiment again, nor can we observe other universes to compare with our own. Furthermore, even within our own universe, different regions might have slightly different properties, especially in the early universe when structures were still forming and the universe was less homogeneous. Imagine trying to understand the entire ecosystem of Earth by observing only a few square meters of a rainforest. You might find a remarkable diversity of life, but would that small patch be truly representative of the entire planet? Similarly, when Webb observes a particular patch of the sky, say the Good South Field or the Cosmos Field, it's looking at a specific region of the early universe. The disturbing question then arises: are these observed fields truly representative of the average conditions in the early universe? Or have we by chance stumbled upon particularly overdense or underdense regions that are not typical? Prior to Webb, our cosmological simulations often assumed a relatively smooth, homogeneous early universe, with small fluctuations that would eventually grow into structures. However, if the regions Webb is observing happen to be exceptionally dense patches, cosmic overdensities, then the accelerated galaxy formation and the abundance of massive galaxies might be partially explained by these local conditions. In an overdense region, there would be more matter available for gravitational collapse, and structures would naturally form faster and grow larger. This would mean that while the findings are still remarkable, they might not be universally applicable to the entire early universe. This doesn't necessarily diminish the disturbing nature of the discoveries, but it shifts the focus of the disturbance. Instead of a fundamental flaw in the lambda CDM model itself, it could point to a more complex and varied early universe than we had previously assumed. It would imply that the universe was not as statistically uniform in its infancy as our models often portray, or that the process of homogenization took longer than expected. This would still require adjustments to our models, perhaps by incorporating more sophisticated treatments of large-scale structure formation and the role of environmental factors. Astronomers are acutely aware of the challenge posed by cosmic variance. To mitigate its effects, they are conducting multiple deep-field surveys across different regions of the sky. By comparing the galaxy populations in these various fields, they hope to build a more statistically robust picture of the early universe. If the abundance of massive early galaxies is consistently found across many independent fields, then the argument for a fundamental revision of our cosmological models becomes much stronger. If, however, there are significant variations between fields, it might suggest that cosmic variance plays a more dominant role than previously thought. Another aspect related to cosmic variance is the progenitor bias. Could it be that the galaxies we are seeing are simply the lucky ones, the ones that happen to form in regions with unusually favorable conditions for rapid growth? If so, then the average galaxy in the early universe might still be small and nascent, as lambda CDM predicts, and we are simply observing the outliers. While this might seem like a less disturbing explanation, it still forces us to confront the limitations of our observational window and the inherent challenges of drawing universal conclusions from limited data. The disturbing element here is the nagging uncertainty. Are we seeing the true face of the early universe, or just a particularly active corner of it? This question underscores the ongoing nature of scientific discovery, where every answer often leads to a new, more complex question. Webb's golden eye is showing us a universe that is not only stranger than we imagined, but also potentially more heterogeneous in its earliest moments, forcing us to grapple with the statistical subtleties of cosmic existence. The unsettling nature of Webb's findings, particularly when considered alongside other cosmological tensions like the Hubble tension, is leading some scientists to ponder a truly radical and profoundly disturbing possibility: that these anomalies are not merely tweaks to the lambda CDM model, but harbingers of new physics beyond our current standard model of particle physics and cosmology. This isn't just about adjusting parameters, it's about the potential for entirely new particles, forces, or even a re-evaluation of the fundamental laws governing the universe. Consider the implications for dark matter. While the lambda CDM model assumes dark matter is cold and non-interacting beyond gravity, what if it possesses more complex properties? Perhaps dark matter particles interact weakly with each other, or with ordinary matter, in ways we haven't yet detected. Such interactions could lead to more efficient cooling and collapse of dark matter halos in the early universe, thereby accelerating the formation of galaxies. Theories like self-interacting dark matter or warm dark matter are being revisited with renewed interest. If dark matter is not perfectly cold, it could suppress the formation of very small structures, but potentially enhance the growth of larger ones, leading to the observed abundance of massive early galaxies. This would mean that the invisible scaffolding of the universe is far more intricate and dynamic than we currently comprehend, with its own hidden physics dictating the pace of cosmic evolution. Then there's the question of dark energy. The cosmological constant, L, in the LCDM model represents a constant energy density permeating all of space. But what if dark energy is not constant? What if it evolves over time? Or if there are additional fields contributing to the universe's accelerated expansion? Theories like quintessence or early dark energy propose dynamic forms of dark energy that could have had a different impact on the universe's expansion rate in its infancy. A different expansion history could directly influence the time available for structures to form, potentially allowing for the rapid growth of the early galaxies Webb observes. If dark energy is more complex, it means the very fabric of space-time is fluctuating in ways we are only beginning to glimpse, with profound implications for the ultimate fate of the universe. More radically still, some researchers are exploring modifications to gravity itself. While Einstein's general relativity has been incredibly successful, it has its limits, perhaps on cosmological scales or in the extreme conditions of the very early universe. Gravity behaves differently than predicted. Theories of modified gravity, e.g., FR gravity, Dvali-Gabadadze, Porati model, attempt to explain cosmic acceleration or structure formation without invoking dark energy or dark matter, or by altering their properties. If gravity is not precisely what we think it is, then the entire gravitational engine-driving galaxy formation could be operating on different rules in the early universe, leading to the disturbing observations from Webb. Such a paradigm shift would be monumental, challenging one of the pillars of modern physics. The disturbing aspect of new physics is that it means our current understanding of the universe which we have painstakingly built over centuries, is fundamentally incomplete. It implies that there are hidden layers to reality, unknown particles, or unseen forces that are actively shaping the cosmos in ways we are only just beginning to detect. Webb's findings are not just pushing the boundaries of our telescopes, they are pushing the boundaries of our imagination, forcing us to consider that the universe is far stranger, far more complex, and far more unsettling than our current theories allow. The search for these answers will undoubtedly lead to a new era of discovery, where the distinction between astrophysics and fundamental physics blurs, and where the universe itself becomes the ultimate laboratory for testing the most profound questions about reality. Behind every scientific discovery, behind every data point, and every theoretical model, lies the human element, the minds, the emotions, the countless hours of dedication, and the intellectual struggle to comprehend the universe. The disturbing findings from Webb are not just abstract scientific problems. They are profoundly impacting the scientists who have dedicated their lives to understanding cosmic evolution. This isn't a detached, dispassionate process. It's a journey filled with awe, frustration, excitement, and sometimes a deep sense of unease. Imagine an astrophysicist who has spent decades working within the Lambda CDM framework, building simulations, analyzing data, and contributing to a coherent picture of the universe. Then, suddenly, a new instrument like Webb comes along and presents data that fundamentally challenges that picture. The initial reaction can be one of disbelief, a natural human tendency to resist information that contradicts deeply held beliefs. There's a rigorous process of checking and rechecking, scrutinizing every step of the observation and analysis to ensure that the anomaly is real and not an error. This period of intense verification is crucial, and it's where the scientific method truly shines. But once the reality of the disturbing findings settles in, it can evoke a range of powerful emotions. For some, it's a thrill, the excitement of being at the forefront of a potential paradigm shift, the chance to rewrite the textbooks and contribute to a deeper understanding of reality. This is the allure of discovery, the intellectual high of confronting the unknown. For others, there can be a sense of frustration, as years of work might need to be re-evaluated or even discarded. It's a humbling experience, a reminder that even our most sophisticated models are just approximations of a universe that is far more complex and surprising than we can ever fully grasp. The ongoing scientific debate is a testament to this human element. Conferences are buzzing with discussions, papers are being published at a rapid pace, and collaborations are forming to tackle these new challenges. It's a dynamic, sometimes contentious, but ultimately productive process. Scientists are not afraid to argue, to challenge each other's interpretations, and to push the boundaries of conventional thinking. This intellectual ferment is essential for progress, as it forces everyone to sharpen their arguments, refine their models, and seek out new evidence. Moreover, these disturbing findings spark a sense of wonder that transcends the purely scientific. They remind us of the vastness of our ignorance and the boundless mysteries that still await us. They connect us to a long lineage of human inquiry, from the ancient stargazers to the modern cosmologists, all grappling with the fundamental questions of existence. The universe, through Webb's golden eye, is not just revealing its physical secrets. It's revealing something about the human spirit itself, our insatiable curiosity, our relentless drive to understand, and our capacity to be disturbed, humbled, and ultimately inspired by the cosmic unknown. The emotional journey of discovery, the intellectual wrestling with disturbing truths, and the collaborative spirit of the scientific community, are all integral parts of this unfolding cosmic drama. It's a story not just of telescopes and galaxies, but of humanity's ongoing quest to understand its place in a universe that continues to defy, disturb, and ultimately delight us with its endless wonders. The term early galaxies might sound generic, but within the disturbing trove of Webb's discoveries, there are specific types and properties that are particularly unsettling. These aren't just any galaxies. They are a collection of cosmic anomalies that collectively scream for a re-evaluation of our models. Let's delve into the specific characteristics that make these early galactic inhabitants so profoundly disturbing. First and foremost is their stellar mass. Prior to Webb, the expectation was that galaxies in the first few 100 million years after the Big Bang would be relatively small, with stellar masses perhaps a few million to a few tens of millions of solar masses. These would be the building blocks of larger galaxies, gradually accumulating mass over cosmic time. However, Webb has consistently found galaxies with stellar masses reaching hundreds of millions, and even billions of solar masses. Some are estimated to be as massive as our own Milky Way, which is a mature galaxy that has accumulated its mass over 13 billion years. The sheer accumulation of stellar mass in such a short cosmic timescale is a direct contradiction of the hierarchical formation scenario predicted by lambda CDM, where such massive systems should simply not have had enough time to assemble. Closely related to their mass is their star formation rate, SFR. To achieve such immense stellar masses so quickly, these galaxies must have been forming stars at an incredibly furious pace. Estimates suggest solar masses of hundreds or even thousands per year. To put this into perspective, our Milky Way currently forms stars at a rate of only a few solar masses per year. This means these early galaxies were cosmic fireworks, exploding with stellar creation at rates far exceeding what our models predict for such an early epoch. What physical mechanisms could have driven such sustained and intense bursts of star formation? Was there an inexhaustible supply of cold gas efficiently funneled into star-forming regions? Or were the conditions in the early universe, such as higher gas densities and different cooling mechanisms, uniquely conducive to such extreme stellar nurseries? Another disturbing property is their metallicity, or the abundance of elements heavier than hydrogen and helium. These metals are forged in the cores of stars and dispersed into the interstellar medium through supernova explosions. For a galaxy to be chemically enriched, multiple generations of massive stars must have lived and died, a process that takes time. Yet, spectroscopic observations from Webb are revealing that some of these early galaxies are already surprisingly metal-rich. This implies an even more rapid cycle of star birth, death, and enrichment than their high stellar masses alone would suggest. It's like finding an ancient forest with mature trees and rich soil, when you expected only saplings and barren ground. This rapid chemical evolution challenges our understanding of how quickly the universe built up the heavy elements necessary for rocky planets and ultimately for life. Furthermore, some of these early galaxies are exhibiting surprisingly regular morphologies. While the earliest galaxies were expected to be irregular, clumpy, and undergoing chaotic mergers, Webb has hinted at the presence of nascent disks and more organized structures in some systems. The formation of a stable rotating disk requires a significant period of gravitational settling and dynamic evolution. To see even the beginnings of such organization in galaxies existing just a few 100 million years after the Big Bang is another unsettling observation, suggesting an accelerated pace of galactic maturation that is deeply challenging to our conventional understanding of galaxy assembly. Finally, the luminosity of these objects is also a key disturbing factor. Many of these early galaxies are incredibly bright, far brighter than expected for their age and size according to lambda CDM. This extreme luminosity can be attributed to their high star formation rates and potentially a different initial mass function, where a higher proportion of massive, luminous stars were formed. This luminosity makes them detectable by Webb, but it also underscores their anomalous nature. They are cosmic lighthouses, shining with an intensity that belies their supposed youth, and their very visibility is a disturbance to our prior expectations. In essence, these early galaxies are not just too massive, too soon. They are too active, too metal-rich, too organized, and too luminous for their cosmic age. Each of these properties, individually, presents a challenge to the lambda CDM model. Taken together, they constitute a profound and deeply disturbing set of observations that demand a fundamental re-evaluation of how and how quickly the universe built its grand structures. The universe, it seems, was in a far greater hurry to grow up than we ever gave it credit for. In the grand cosmic ballet of galaxy evolution, mergers and feedback mechanisms play pivotal roles. Galaxies are not isolated islands. They interact, collide, and merge, a process that can trigger bursts of star formation and reshape their structures. Simultaneously, feedback from supernovae and active galactic nuclei, AGN, can regulate star formation, expelling gas and preventing runaway growth. Our lambda CDM model incorporates these processes, but Webb's disturbing findings suggest that their dynamics in the early universe might have been far more complex or even fundamentally different than previously assumed. Cosmic mergers. In the hierarchical model of galaxy formation, mergers are a key driver of growth. Small galaxies merge to form larger ones, and these mergers can funnel gas towards the galactic center, triggering intense bursts of star formation. However, the sheer abundance of massive galaxies so early in the universe presents a puzzle. For these galaxies to have reached such immense stellar masses, they would have needed to undergo numerous mergers in a very short cosmic timeframe. This implies a much higher merger rate in the early universe than our simulations typically predict, or that the mergers themselves were exceptionally efficient at building stellar mass. What makes this disturbing is that frequent chaotic mergers in the early universe should, in theory, lead to irregular, disturbed morphologies. While some early galaxies observed by Webb are indeed irregular, others show surprisingly ordered structures, or at least the beginnings of them. This tension suggests that either the mergers were less disruptive than anticipated, or that the processes of restabilization and disk formation were incredibly rapid. It could also imply that the early universe was not just a place of frequent mergers, but of efficient mergers, where gas was quickly converted into stars rather than being ejected. Feedback mechanisms. Feedback, the process by which energy and momentum from star formation and AGN activity regulate galaxy growth, is another area where Webb's observations are causing disturbance. Supernovae, the explosive deaths of massive stars, can drive powerful winds that expel gas from galaxies, thereby shutting down star formation. Similarly, active supermassive black holes at the centers of galaxies can launch powerful jets and winds that heat and push away gas, preventing it from cooling and forming new stars. These feedback mechanisms are crucial for preventing galaxies from growing too large too quickly in our models. However, if the early galaxies observed by Webb were forming stars at such prodigious rates and growing so massive, it suggests that feedback mechanisms might have been less effective in their infancy. What could account for this? Perhaps the gas in the early universe was denser, making it harder for winds to escape. Or maybe the stellar populations in these early galaxies had a different initial mass function, with fewer massive stars that explode as supernovae, thereby reducing the impact of stellar feedback. Alternatively, the feedback from early AGN might have been channeled differently, perhaps stimulating star formation in some regions while suppressing it in others, leading to a more complex interplay than our current models capture. The disturbing implication is that the delicate balance between gas infall, star formation, and feedback, which governs galaxy evolution, might have been fundamentally different in the early universe. Our current models, calibrated to observations of the local universe, might not be accurately capturing these processes in the extreme conditions of the cosmic dawn. Webb's observations are forcing us to reconsider the strength, efficiency, and nature of these cosmic forces, suggesting that the early universe was a much more complex and dynamic arena, where galaxies were built with an efficiency and speed that continues to baffle and disturb our scientific understanding. The interplay of mergers and feedback, once thought to be well understood, is now another layer of cosmic mystery unveiled by Webb's golden eye. Beyond the scientific equations, the intricate data analysis, and the complex theoretical models, the disturbing discoveries from the James Webb Space Telescope carry profound philosophical implications. They force us to confront not just the limits of our scientific models, but the very boundaries of human perception, our inherent biases, and our often anthropocentric view of the universe. For millennia, humanity has sought to understand its place in the cosmos, often constructing narratives that place us at the center, or at least within a predictable, comprehensible framework. These new findings shatter that comfortable predictability, reminding us of the universe's boundless capacity for surprise and its indifference to our preconceived notions. One of the most striking philosophical takeaways is the reinforcement of scientific humility. For decades, the Lambda CDM model has been extraordinarily successful, leading many to believe that we were converging on a nearly complete understanding of cosmic evolution. While the model remains robust in many aspects, these early galaxy discoveries serve as a powerful reminder that our knowledge is always provisional, always subject to revision in the face of new, compelling evidence. It's a humbling experience for the scientific community, a call to remain open-minded and to constantly question even our most cherished theories. The universe doesn't care about our elegance or simplicity. It simply is, and our task is to listen to what it tells us, however unexpected or disturbing that message may be. These discoveries also challenge our perception of time and scale. We, as humans, operate on timescales of decades and centuries. Even geological time, spanning millions of years, is difficult to fully grasp. But cosmic time, with its billions of years, is almost unfathomable. The idea that galaxies could form so rapidly, reaching maturity in a mere few 100 million years, compresses our sense of cosmic development. It suggests that the early universe was not a slow, languid process, but a period of intense, almost frenetic activity. This accelerated timeline forces us to recalibrate our mental models of cosmic evolution, making us realize that the universe's infancy was far more dynamic and eventful than previously imagined. Furthermore, the sheer beauty and complexity of these early structures observed so far back in time, evoke a sense of awe that transcends mere scientific curiosity. They are luminous beacons from a distant past, whispering tales of creation and evolution that are both familiar and alien. They remind us that the universe is not just a collection of physical laws and particles, but a canvas of unimaginable grandeur, constantly unfolding in ways that defy our expectations. This aesthetic and emotional impact is a crucial, often unstated aspect of scientific discovery, connecting us to the cosmos on a deeper, more personal level. The existence of these disturbing galaxies also sparks questions about the uniqueness of our own cosmic history. If galaxy formation was so efficient and widespread in the early universe, does that imply that conditions for life could have arisen much earlier than previously thought? While life requires specific conditions and the presence of heavier elements, the rapid chemical enrichment observed in some of these early galaxies suggests that the building blocks for complex chemistry might have been available surprisingly early. This opens up tantalizing possibilities for the existence of early extraterrestrial life, pushing the timeline for abiogenesis further back into cosmic history. In essence, Webb's findings are not just about galaxies, they are about us. They are about our capacity to observe, to theorize, to be surprised, and to continually expand our understanding of the universe we inhabit. They are a powerful testament to the human spirit of inquiry, a reminder that the greatest discoveries often lie just beyond the edge of our current knowledge, waiting to be unveiled by instruments like Webb and the minds brave enough to interpret their revolutionary messages. The universe, in its infinite wisdom, continues to teach us humility, wonder, and the enduring power of scientific exploration. The current state of cosmology, characterized by these disturbing findings from Webb, is not a dead end but a vibrant frontier. It is a testament to the fact that the universe continues to hold secrets far beyond our current grasp, and that our journey of discovery is far from over. The path forward will involve a multi-pronged approach, combining even more powerful observational tools with radical theoretical advancements, all aimed at resolving the unsettling puzzles that Webb has so brilliantly illuminated. On the observational front, the James Webb Space Telescope will continue to be our primary window into the early universe. Its ongoing deep field surveys will expand the sample size of these early galaxies, allowing for more robust statistical analyses and a clearer picture of their distribution and properties. Future observing cycles will focus on obtaining more spectroscopic data for these critical objects, providing definitive measurements of their redshifts, stellar masses, chemical compositions, and internal dynamics. This detailed spectroscopic follow-up is essential for distinguishing between various theoretical explanations and for refining our understanding of star formation and feedback processes in the cosmic dawn. Beyond Webb, the next generation of observatories is already on the horizon, promising even more revolutionary insights. The Nancy Grace Roman Space Telescope, set to launch later this decade, will offer an unparalleled wide-field view of the infrared sky. While Webb excels at deep narrow-field observations, Roman will be a cosmic cartographer, mapping vast swathes of the universe with its immense field of view. This will be crucial for understanding the large-scale distribution of these early galaxies and for mitigating the effects of cosmic variance. By surveying larger volumes of the early universe, Roman will help us determine if the regions Webb has observed are truly representative or if they are exceptional cosmic overdensities. On the ground, the extremely large telescopes, ELTs, such as the European Extremely Large Telescope, EELT, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, are under construction. These colossal telescopes, with mirrors ranging from 25 to 39 meters in diameter, will be equipped with advanced adaptive optic systems to compensate for atmospheric distortion. While they cannot observe in the infrared as effectively as Webb due to atmospheric absorption, they will be invaluable for obtaining high-resolution spectroscopy of slightly less distant but still early galaxies. Their immense light-gathering power will allow for detailed studies of galactic kinematics, gas flows, and the distribution of dark matter, providing complementary data to Webb's observations. On the theoretical side, the disturbing findings are spurring a renaissance in cosmological modeling. Theoreticians are actively developing new simulations that explore alternative scenarios for galaxy formation, incorporating more efficient star formation, different dark matter properties, or modified gravitational physics. These simulations will need to be capable of reproducing the observed properties of these early galaxies, while also remaining consistent with all other cosmological observations. The interplay between these new theoretical models and the ever-growing observational data will be a dynamic process, with each informing and challenging the other. Furthermore, the search for new physics will intensify. If the current anomalies cannot be resolved by refining existing models, then the scientific community will be forced to seriously consider more radical solutions. This could involve the discovery of new particles, new fundamental forces, or even a re-evaluation of the nature of space-time itself. The Hubble tension, in particular, continues to be a persistent thorn in the side of lambda CDM, and its resolution might require a deeper understanding of the universe's fundamental constituents and their interactions. The convergence of these two disturbing problems, early galaxies and the Hubble tension, suggests that we might be on the cusp of a profound paradigm shift in cosmology, one that could redefine our understanding of the universe's fundamental laws. Ultimately, the future of cosmology is one of boundless potential. The disturbing discoveries from Webb are not a cause for despair, but a powerful catalyst for intellectual growth and scientific advancement. They remind us that the universe is far from a solved puzzle, and that its deepest secrets are often hidden in the most unexpected places. As we continue to push the boundaries of technology and theoretical understanding, we are not just learning about galaxies and black holes. We are learning about the very fabric of reality, about the forces that shaped everything we know, and about our own place in this grand, unfolding cosmic drama. The adventure of discovery continues, and with every new photon captured by Webb, the universe whispers another secret, inviting us to listen, to learn, and to be amazed. As our cosmic journey through the unsettling revelations of the James Webb Space Telescope draws to a close, we are left with a profound sense of wonder, tinged with a healthy dose of intellectual disquiet. Webb, designed to illuminate the universe's earliest moments, has instead found shadows where there should have been light, and complexities that defy our most cherished models. The disturbance isn't a fleeting anomaly. It's a persistent whisper from the cosmic dawn, challenging the very foundations of our understanding. We've confronted the unsettling reality of massive, mature galaxies existing in a cosmic infancy, defying the gradual timeline predicted by the Lambda CDM model. We've grappled with their furious star formation rates, their surprising chemical enrichment, and their hints of organized structures, all properties that scream too much, too soon. We've explored the radical notion of dark stars powered by the unseen hand of dark matter as a potential explanation for these luminous enigmas. We've seen how these early galaxy problems intertwine with the perplexing Hubble tension, suggesting a deeper systemic crisis in our cosmological framework. We've journeyed through the historical echoes of scientific paradigm shifts, reminding ourselves that moments of disturbance are often the catalysts for humanity's greatest leaps in understanding. We've acknowledged the human element in this grand quest, the initial skepticism, the subsequent awe, and the ongoing, passionate debate that characterizes a vibrant scientific community. And we've looked to the future, to the next generation of telescopes and theoretical models that will undoubtedly be shaped by the unsettling truths Webb has uncovered. Ultimately, what Webb has found is disturbing not because it points to a flaw in the telescope itself, or even necessarily a flaw in the universe. It is disturbing because it points to a profound incompleteness in our understanding. It forces us to confront the limits of our knowledge, to shed the comfort of established theories, and to embrace a universe that is far more complex, far more dynamic, and far more mysterious than we ever dared to imagine. It is a universe that refuses to be neatly categorized, a universe that constantly challenges our intellect and expands our consciousness. So, what does this mean for us, here on our pale blue dot, nestled in a galaxy that itself was once a cosmic infant? It means that we are living in an extraordinary time, a period of unprecedented discovery where the very fabric of reality is being re-examined. It means that the cosmos is a place of boundless wonder, where the most profound truths are often hidden in the faintest whispers of light from the dawn of time. And it means that the human spirit of inquiry, our relentless desire to know, is our most powerful tool for unraveling the universe's deepest, most disturbing secrets. If this journey into the unsettling truths revealed by the James Webb Space Telescope has ignited your curiosity, if the thought of these cosmic mysteries resonates with your own sense of wonder, then I invite you to join us on this ongoing adventure. The universe is a vast and beautiful place, and there are still so many stories to tell, so many disturbing truths waiting to be unveiled. Thank you for joining Cosmodepth on this incredible voyage through space and time. If you found this exploration compelling, please consider liking this video, sharing it with fellow cosmic enthusiasts, and subscribing to our channel for more journeys to the edge of cosmic knowledge. Your support helps us continue to bring these captivating and sometimes unsettling stories of discovery to light. Until our next cosmic adventure, keep your eyes on the stars and never stop questioning the depths of the cosmos. Before the revelations from Webb, the period between the Big Bang and the epoch of reionization was often referred to as the Cosmic Dark Ages. This wasn't a period of literal darkness, as the universe was still filled with photons, but rather a time when the universe was largely devoid of luminous sources like stars and galaxies. After the initial burst of light from the Big Bang, the universe cooled sufficiently for protons and electrons to combine and form neutral hydrogen atoms. This neutral hydrogen, being opaque to ultraviolet light, effectively shrouded the universe in a dense, obscuring fog. During this era, gravity was slowly working to pull together the first clumps of matter, but the formation of significant luminous structures was thought to be a slow, gradual process, leading to a relatively quiet and uneventful cosmic landscape. Our previous models depicted the cosmic dark ages as a time of serene, almost uneventful waiting, a period where the seeds of future galaxies were sown, but where the universe itself was largely unlit, a vast expanse of neutral gas patiently awaiting the dawn of the first stars. This narrative of a quiet, slow-burning infancy was a cornerstone of our cosmological understanding, providing a clear, logical progression from the Big Bang to the complex universe we see today. The gradual emergence of small, faint galaxies was supposed to be the first flickering lights that would eventually end this period of cosmic obscurity. However, Webb's disturbing findings are forcing us to radically redefine this dark age. If massive, luminous galaxies were already forming stars at prodigious rates just 300 to 500 million years after the Big Bang, then the cosmic dark ages were not so dark after all. Instead of a quiet, unlit nursery, Webb is revealing a bustling, vibrant, and surprisingly active period. It suggests that the universe was already lighting up with powerful galactic beacons much earlier and with far greater intensity than we had ever dared to imagine. This redefinition is profoundly unsettling because it means our entire timeline of cosmic luminosity and structure formation might need to be shifted, or at least recalibrated. The implications are far-reaching. If the cosmic dark ages were punctuated by these bright early galaxies, then the very process of reionization, the clearing of the neutral hydrogen fog, might have been initiated and completed much earlier, or in a different manner than previously theorized. These early galaxies would have been powerful sources of the ultraviolet photons needed to ionize the neutral hydrogen, potentially carving out large bubbles of transparency in the cosmic fog much sooner. This would mean that the Dark Ages were perhaps more of a twilight period, with significant sources of light already illuminating the nascent cosmos. This re-evaluation of the cosmic Dark Ages is a direct consequence of Webb's unparalleled sensitivity and its ability to peer through the veil of red-shifted light. It's a testament to the fact that our scientific models, while powerful, are always provisional, always subject to revision in the face of new, compelling evidence. The universe, it seems, was in a much greater hurry to light up than we had previously believed. And this accelerated timeline for cosmic illumination is yet another disturbing piece of the puzzle that Webb is assembling. The cosmic dark ages, once a period of theoretical calm, are now revealed as a dynamic and surprisingly eventful chapter in the universe's grand story, forcing us to rethink the very beginning of cosmic light.